K-map.
If you have ever programmed in C, then you've definitely come across the function malloc. It is used to allocate and free memory dynamically. But what does that actually mean? It means that memory is allocated at runtime instead of compile time. But where does this memory come from? Memory is allocated in the heap. How does your memory ask the operating system for it? And once allocated, how is this memory tracked, managed, and eventually freed? In this lecture, we are going to go beyond just using malloc. We're going to understand how it actually works internally by designing and implementing one ourselves. Now, it is important to note that the real world memory allocators, like the ones used in modern operating systems, are highly optimized and designed to handle complex scenarios like multi-threading and performance. The purpose of the memory allocator we are building is simply to get a grasp on the concepts of memory allocation while building one ourselves. So let's get started. To truly understand malloc, we first need to ask a more fundamental question. What is the difference between static memory and dynamic memory? Static memory is allocated at compile time. Its size is known in advance and it remains fixed throughout the execution of the program. You can take the example of a global variable or a fixed size array. For example, here we've taken the example of an integer variable which is being declared in a static way. The memory which is allocated here is done at compile time and it remains throughout the execution of the program. Therefore, it's called static memory. On the other hand, dynamic memory is allocated at runtime. This means your program can request memory when it needs it and release it when it's no longer required. This flexibility is powerful but also introduces complexity. And that complexity is handled by something called the memory allocator, which we will study further in the lecture. Here you can see that the memory which is dynamically allocated, we are allocating the memory whose size is equal to the size of an integer data type. And here it returns a void pointer to that memory region which we are typecasting to an integer variable so that we can easily read the variable later through this pointer. This is a pointer to an integer variable. To understand how memory allocation works, we first need to understand how a memory stores and views memory. The diagram shown here represents the virtual memory layout of a process. If you recall from operating systems, each process, which is simply a program in execution, gets its own virtual address space. This means that from the program's perspective, it appears as if it has access to a continuous block of memory. What we are seeing here is a logical view of the memory. In reality, memory is not necessarily stored contiguously in the physical RAM. In reality, memory may be stored in a non-contiguous way. Some part of it may be stored here, some part of it, I'm sorry for my drawing, some part of it may be stored here. But in the logical view of the memory, it appears that as if it is contiguous. And it is mapped from here to the physical memory through a process called paging. So this diagram is an abstraction. It helps us understand how memory is organized from the program's point of view. And for our purposes, it is perfectly fine to think of memory in this structured way. Now within this virtual address space, memory is divided into multiple sections. At the bottom we have the text section, which stores the compiled machine instructions of the program, the actual code that the CPU executes in binary. Above that is the data section, which stores the initialized variables, the static or the global initialized variables. Next we have the BSS section, the block separated by symbol, which contains the uninitialized variables or the variables which are initialized by the value 0. At the top we have the stack. The stack is used for function calls. Each time a function is called, a new stack frame is created. Each time the stack is called, a new frame is created. The frame stores function arguments, local variables, and return addresses, and also base pointers. You can think of the stack as a temporary workspace for functions. In recursive calls, the stack keeps track of each function invocation separately. The stack grows downward. Here it's shown downward. Technically, it makes no sense to say downward or upward, but we can say that the stack and the heap grow in opposite directions. That would be a better way to frame it. But we can say that the stack grows downward. Next, we have the heap. This is where dynamic memory lives, memory that we allocate using functions like malloc. As you can see, the heap grows upward as we request for more memory during runtime. Now, here's a very important observation. Stack and the heap grow in opposite directions. They move towards each other. This is mainly an optimization strategy for maximizing the available space in the logical memory, in the virtual address space available to that process. So if they collide, the program runs out of memory, and this is a smart way to manage memory. Finally, let's talk about an important concept called the program break. Sometimes the data, the BSS, and the heap are together known as the data segment. The end of the heap is marked by this pointer called the break or the program break pointer. It is denoted by BRK. This pointer tells us where the heap currently ends. When we request more memory using low-level system calls, the operating system simply moves the program break forward, and when we free the memory, it moves the program break back. And that is how the heap grows dynamically. In this lecture, we are running Linux, so we can make use of the sbrk system call that lets us manipulate the program break. By putting 0 in the parameter of sbrk, it gives us the current address that the program break pointer is pointing to in the memory of the heap. If we put a positive value in the parameter of the sbrk system call, it increments the break pointer by a value of that many bytes which is present in the parameter. So in this case, it will increment it by 30 bytes. So 1000 plus 30 is, it will point to the address 1030. The program break pointer will point to the address 1030. If we put a negative value in the parameter, it will decrement the break pointer by that many bytes. So it will decrement the pointer break by 15 bytes here. So it will point to 1015. In case of failure, the sbrk function simply returns a void pointer to -1. To be honest, the sbrk is not the best choice. There are better alternatives like the mmap available today. But for the purpose of this video, sbrk does the job. Okay, so I've written the code out for you. We're going to test out how the sbrk is working practically. I've included the necessary libraries here. I'm storing the initial value, the initial address that it is the program break pointer is pointing to in this variable. I'm typecasting it to integer pointer instead of a void pointer, so that it's easier to read the address. Otherwise, it would be in a hexadecimal form. It would be tough to decipher the changes. So after that, I'm incrementing it by 5 bytes, the program break pointer. Then I'm storing the value of the address that it is pointing to after the increment and after increment. Then I'm decrementing it, or rather freeing the memory, you can say, by 3 bytes. Again, I'm storing it. Then I'm printing all the addresses just to show you the changes. So let's go and run this. Let's compile this first. Let's run the file. So here's the output. The current address, the initial it was pointing to, let's just read the last 2 digits, 00. After incrementing it, it's 05. And after decrementing it by 3 bytes, or rather freeing the memory, is pointing to 02 bytes. That's all. Okay. So now we're going to make a simpler version of malloc on our own. So let's start coding the malloc file. We're going to call it sasta malloc. Let's start coding it up. We're going to make a function here. Let's call the function also sasta malloc, because I don't want it to interfere with the original malloc function, which is in the standard library. And it will have a variable size t specified by the user. We're going to call this malloc function from another program file called the main file. I'll create it later. and it will return a void pointer, uh, and it will point towards the memory block which it has allocated, the end of the memory block. It will return a void pointer. Okay, so inside this we will call the s break function. Okay, I have to input the library for this, and we want, how much memory do we want to allocate? We want to allocate the size which will be specified by the user. We will store it in a void pointer variable called block, and let's say if we will return the point block pointer unless if, like I said, in case of error the sbrk returns a void pointer to -1. If block is void pointer to -1, then we will return null. Let's see what are the necessary libraries we need to import. I think we're gonna need to include h. This is for the sbrk. Gonna need uh, for the size t. We're gonna need standard int library. So everything seems right. If there's any error, we'll solve it later. Okay, so that one's done. Now we make the header file for this because we'll forget it later. Let's make a file called system.malloc.h. Now we will put in some header guards here. All header guards does is it prevents the computer from adding the files, running the files twice. Even if it adds the file while compiling, it prevents it from running it multiple times, thus saving CPU cycles. Okay, so here we will, if not defined, we'll give it a name. Let's say system. Oh, there's like a key define. This is when, if it is not defined, then they will define it. Like first time they are compiling it, they will define it as system h. But if it is already defined, then this will catch it and it will prevent it from running it again and again. And within this, we'll just declare functions. First one, yeah, void pointer. And I think inside it was the data type size. Name was size. That seems right for now. Okay, now we'll code the main file. Yeah, I'll code the main file. The main, let's include the standard library. I write these before because I have a habit of forgetting these and it leads to error. Okay, so here we will call our system malloc function with size, let's say 5. We can give a user input also here by asking the user how much memory we want to allocate, but for now I'm keeping it simple, and I'll keep it in a void pointer, or let's also name this block. Okay, and okay, so we won't know what a system malloc is, so we'll have to include the header file. So system block page. Okay, now we will point. Okay, this time I'm not typecasting it to integer pointer variable like I had done in the previous video. Previous section in which I typecasted the word pointer variable into an integer variable just to show you the difference of how the pointer was changing as I called the sbrk function. Here I'm not doing that, so you will see the address in hexadecimal form itself. So let's print it up. The address of the end of the allocated block is, say, B. Okay, so everything seems right for now. Let's run it and see. Let's compile it. Well, since this is a small program, we'll compile it together and make the output file a program called, make the output file something called my program or something. Sus log dot c, and the output binary file we'll call it my program. Okay. Okay, of course, there's an error. What? Oh, sorry, there won't be an underscore. Let's change that. Sorry, I had made a small error in the system malloc file. So I gave an underscore here in the standard in part, so I cleared that off. Now let's compile it again. And we're gonna save it a binary file. Save it as a binary file called my program. Okay, it runs nicely. Now let's run it. Okay, so our function that we made called system malloc, it allocated a memory block, and the address of the end of the allocated block is this in hexadecimal form. So till now we have just arranged our file structure and made a simple baby memory allocator, which on being called with a parameter of, let's say, 100 is allocating 100 contiguous bytes. But it is just too simple to be true. This architecture of malloc simply does not work, as we learn in the next section that we need pointers to memory blocks to know how much and where to release memory from when we call the free function. So we are following an evolutionary model of building the software where we build on top of the existing structure as the requirements change. Also, I should have mentioned earlier that the sbrk I am using is a Linux based system call, so it will not work in Windows command line or WSL. If you don't have Linux, you can use an online Linux terminal like I am doing to work without hassle. I will put a link in the description. Now we move on to free. Let's say someone wants to free up memory and calls the free function with the pointer p in the parameter. See that it only gets a pointer, not the size. So how does free function know how much memory to free? This is a problem because memory is just raw bytes. If free function is called, it does not know whether it should release 50 bytes or 100 bytes. That's because pointer alone is not enough to describe a memory block. We also need the size, otherwise we don't know how much memory to free. So we store the size somewhere. We store the size just before the memory block in a header. Therefore, during malloc, we ask for extra memory and store the size in metadata, that is the header. Therefore, the total size becomes the metadata plus the size of the memory region. The pointer p is pointed to the first block after the header, and or you can say the first block of memory region, and then return. During free, we just move the pointer backward, read the stored data, read the stored size of the memory region, free up that amount of memory. Therefore, to sum it up, free cannot work unless we know the size of the memory block. In addition to that, the heap memory is contiguous, so we can only release memory which is at the end of the heap. And since the user only gives us pointer, we must secretly store the size ourselves. That is why every allocator adds a hidden header before the memory block. The idea is simple. When a program requests for X bytes of memory, we calculate the total size as header size plus X and call sbrk total size. To store this information, we will add a header to every newly allocated memory block. The header will look something like this. It will contain the size of the memory block of the actual memory region. So 100 bytes. That means this red region is 100 bytes. It will also contain a variable to check if that memory block is free or is already allocated. So if it is free, then it will say yes. If it is already allocated, like we have, it's not free. There are bits here, so it says no. One important thing is we can't be completely sure if the blocks of memory allocated by our malloc is contiguous. We also need to find a way to traverse through our blocks for memory. Therefore, we need to keep track of the memory allocated by our malloc. Therefore, we turn them into a linked list. Hence the next pointer here. This will be easier to understand now. We'll put them in a linked list, each memory block. So it is essentially a linked list of memory blocks. We will have a head. Sorry. We will have a head and a tail pointer to keep track of the list. Okay, so now we're going to start coding up the header structure. Let's make a structure called header. Inside it, we'll add 3 metadata. First will be the size of the allocated memory region. It will be of the data type size t instead of integer, because integer can hold negative values and memory regions can never hold negative values. So size t is a better data type for it. Next, we will have the is free variable, which will be of the unsigned data type. This will just tell us if the allocated memory region is free or is already allocated. And third, we'll have a pointer to the next header of the next memory region. We'll call it next, the pointer. It will be a pointer to another header structure. So everything seems alright. Okay, now if you don't know how a union in C works, I will suggest you look it up, because others on YouTube have explained it in a better way. Basically, what we do is, in a union, the size of a union is the largest of its members. So if there are two members inside a union, let's say integer and a character, an integer takes 2 bytes and a character takes 1 byte. So the size of the union will be the larger of its members. So larger one is int. So it will take 2 bytes. So it's just a clever way of managing memory. So what we'll do is we'll wrap this around in a union data structure, so that the size of the header is always constant. It is always 16 bytes. How we'll do it, I'll tell you while coding it. So let's make a union called header, and we'll put the structure inside this. It won't have a name after entry, so we'll remove this. We'll wrap the structure in this. Right. Let me just make the indentation properly. Okay. Now what we'll do is we'll put the second item in the header as a array of characters of 16 characters. So each character takes 1 byte. So 16 into 1, it will take 16 bytes. Why we are doing it is so that it always remains constant. The size of the header always remains constant. Otherwise, when we are returning the pointer to the memory, at the end of the header, we are returning the pointer. That needs to be constant. Otherwise, it will create many issues. So what we'll do is we'll create a character array of, let's say the name is padding of 16 bytes. So if let's say the structure occupies less than 16 bytes, then this will make its size 16 bytes. And in case the structure occupies more than 16 bytes, then it will, let's say the structure is of 17 bytes, then the union header will occupy 17 bytes, because then the structure will be the maximum size of these two. It's either the structure or this array. Okay, we'll add an alias to the structure here called s so that we can easily access it, and we'll also create an alias for the union header so that it's easier to create variables of that kind. So we'll create an alias for union header. We'll call it header, let's say underscore t. So that seems alright for now. One more thing I forgot to add, that is this pointer will not be a pointer to a structure header, no, it will be a pointer to a union header. That's a small change. Okay, so here we have a diagram of the how the memory blocks are arranged. These may or may not be contiguous. This is basically a linked list of memory regions. But we will need a pointer to the first memory region so that we know from where should we start traversing the memory region. For that, we make a pointer called the head pointer. It will be of the type header t or the union header type. Uh, so you make a pointer. So, also, in case we are traveling the entire memory region, how will we know that we have reached the last memory block? So for that we use a tail pointer. The last memory region points to the tail pointer. The header of the last memory region points to the tail pointer. So we'll also make a tail pointer. That's all. To prevent two or more threads from concurrently accessing the memory, we will put a basic locking mechanism in place. We'll have a global lock, and before every action on memory, we have to acquire the lock, and once we are done, we'll simply release the lock. So let's code it up. Let's call it global lock. We will acquire it and release it to ensure concurrent program.
Okay. So now we alter the malloc code to allocate memory in this new linked list architecture that we have created. Let's walk through how this implementation of malloc works step by step. So first we handle the case where if the size given by the user is 0, then we don't allocate anything and we just return null. Let's code it up. If the size is 0, then we just return. I have switched to VS Code because it's easier to code here than in that terminal. I'll just upload this code file there and then I'll run it on a terminal. You might see that there's wriggles under this and it's showing a warning error. That's because I'm doing this in a Windows environment, but I'll upload this in the simulator where it will run in a Linux environment, so that won't be an issue. Next, we acquire a global lock. This is important because memory allocation is a shared resource, and we want to prevent multiple threads from modifying it at the same time, because it can lead to inconsistency issues if multiple threads allocate at the same time. So let's code it up. Acquire the lock here. The name of the lock is global lock. Now, this part is important. We basically have two cases to handle. Either the memory is already allocated and has a free block available among them, which can accommodate the requested data size. So we can just put the data in that block. So let's divide it into two cases. Case 1, where memory block already available in heap. Free memory block is already available. Keep in mind that this memory block has to be able to accommodate this amount of data of this size. Only then it will fall in case 1. In case 2, there's no free memory, or there's no free memory which is big enough to accommodate the memory. There's no free memory in which the block size is big enough to accommodate the data of this size. Then it will fall in case 2, where there's no free memory available. So in the second case, none of the blocks are free, and we have to request more memory from the OS and create a new memory block there, and then we link it to the other link. Then we link it to the linked list of memory blocks. Now we call a function called the fetch free block and check if a memory block is available. If it is available, a pointer to the first free memory block is returned by the function. If a free block is not available, it simply returns null. Okay, so let's code it up. We'll call the function. Let's call the function fetch free block, and we have to mention the size of the block we want, size of the data rather, that we want to put in there, and we'll store it in the header variable. Okay, so what is the header? The header is basically a pointer which will point to the metadata of the memory block. We create it here. It will be of the data type header t that we had already created here. Sorry, here, the union header kind. We'll call it header, and it will be of the type this. Sorry, it will be a pointer. So now internally, what this fetch function does is it traverses a linked list of the memory blocks and tries to find a block which is marked as free and is large enough to accommodate the requested memory size. It returns a pointer to the first free satisfying memory block. The approach that it uses is the first fit strategy. If such a block is found, we mark it as not free, release the lock, and then return it to the caller. So let's write this function now. Okay, so we write the function. The function to check if free block is available. Okay, so it will return a header, pointer to a header. Let's call the function fetch free block, and it will have the size of the block that we want, size t. We'll call the variable size. Okay, so inside we are traversing a linked list of memory blocks. So let's create another pointer to a header t variable called the current variable. Okay, and first it will have the head pointer. It will point to the head pointer, the first node. Sorry, it will have a pointer. It will be a pointer. Next, we will traverse the list. So while current is not null, at each node we will check. Okay, if the current memory block structure uh, is free, and if the current memory block's structure size is greater than or equal to the memory size that is requested, that means the size. If that happens, then we will return the current pointer. Otherwise, we'll just keep on traversing. Uh, so otherwise, it will just be current is equals to current Yes. And if after traversing the entire, I think this will be, this is fine, it will be none. And after traversing the entire list, if we are not able to find any free memory block, then we will simply return null. Okay, so this function is coded. It will just check if free memory block is available in the heap memory. Now, back in the malloc, we just check if the block was actually allocated. And if it is, then we set it as no longer free and we release the global lock. So first we write the code for the case one. If header is not null, then we'll set it as free. Sorry, it will be headers structure is free. Then we'll release the lock. This is a system call, what I'm writing. Pre-thread mutex unlock. It'll unlock the global lock. And at last, we'll return a pointer to header. Actually, we won't return a pointer to the header. We'll return a pointer to the end of the header or the memory region just after the header ends. And I'll tell you why we're doing this. So it'll be header plus one. And we want it to be in a void pointer format. So we'll typecast it to a word pointer. Okay, now I'll explain why we are returning header plus one. So as we discussed before, that each block of memory actually has a header stored just before it, which contains metadata like the size, whether it is free or not, and the pointer to the next block of memory. We don't want the user to see this header, as it can be a security threat. So instead of returning the start of the block, we return an address just after the header. This pointer. That's what this expression does. The header plus one. It moves the pointer forward by one header, so the caller only sees the usable memory. Okay, now we handle the second case. So if no suitable free block is found, we need to request more memory from the operating system. To do this, we calculate the total size required. This includes both the requested memory and the size of the header. So we compute the total size as size of the header plus the size given by the user. So total size will be the header t data type plus size given by the user. Now we declare this total size variable. It will be of the data type size t. Now we call the sbrk function with the total size variable inside it. Sorry, it should be total size. Next we call the sbrk function, total size variable inside it, so that it allocates more memory in the heap and returns the pointer to the newly allocated memory, and will store it in a block, in a block pointer. And we'll declare this block pointer here. This will be a void pointer. Okay, now if this call fails, it will return a void pointer to -1, as we have talked about before. Uh, if that happens, then we will simply release the lock and return null. So let's do that here. If this break fails, allocate memory, then okay. So how we'll check it is block equals to void pointer to -1. Then we'll release the lock and we will return null. Otherwise, that means the memory has been allocated, and we will use this to set up a new block. The beginning of this memory is used for the header. So the beginning of the memory will be used for the header. So in this case, is break as allocated, so new memory in the okay. So the beginning of the block will be the header. So we'll specify the header as block. Okay, now we will fill in the metadata. So there were three metadata: the header structure dot size will be equal to the size of the data, not the total size, the data given by the user. The header will no longer be free because we are already allocating memory. So is free 0. And for now, there is no other block. So the next, it will not link to any block after that. In null. Next, we will insert this block, the block we have created, into the linked list of the entire memory region. So one edge case is, let's say this is the first block, and there's no other blocks. Then this will be the head block. The head pointer will point to this block. So if there is no head block, that means head is null. Then this will become the head block, equal to header. Otherwise, we attach it to the end of the list using tail pointer. So if tail exists, since tail is also not null, then the tail pointers next will be this block, the current block we have created. Then finally we update the tail to point to this new block, because this new block will become the tail, the last block in the entire memory linked list. Okay, now everything is set up. Finally, we will release the lock. And just like before, we will return the header plus 1. I've already said why we are doing this, for security purpose, and we'll typecast it to a void pointer. Okay, so overall, malloc first tries to reuse existing memory, and if that fails, it requests for more memory from the operating system.
Okay, now we check if this block pointer is at the end of the heap. To do that, we compute the end of the block. We take the starting address of the block. This pointer is pointing to the first actual memory region, rather end of the metadata. We add its size, this thing, 10 bytes, which can be given by the header dot structure size, which is stored in here. The size of this 10 bytes is stored in the here. Okay, and we compare it to the program break. The program break will point to the end of the heap. Let's suppose this entire thing is the heap, then the program break will point here at the end of the heap. If they are equal, then this block is the last block in the heap. Now that we have implemented malloc, let us look at the other half of memory management, free. In this free function, we give it a pointer and it releases the memory. There are two possible cases when we free memory. Let's start coding it up. The first case is where the block is at the end of the heap. In that case, we can actually shrink the heap and return the memory to the OS. So
And the second case is where the block is in the middle of the linked list. We in this second case we cannot release it directly. Instead, we just mark it as free, and it gets overwritten later when someone calls malloc, and that block is allocated. Okay, so in the free function we provide it a block pointer, which is a void pointer type, and that block it frees. This is the same pointer which was returned by the malloc, by the way. Okay, next, first we handle a edge case. If the block pointer is null, then we simply return. Uh, then we will acquire the lock. Now comes a very important step. The pointer we receive in the block pointer, points to the user memory, not the metadata, or not the header. But we know that the header is stored just before the memory. So we cause the pointer to a header pointer and move one unit backward. That gives us access to the metadata of the block. So the header will be the block pointer. We'll typecast it to a header t pointer and move one place backward. Okay, we also declare this header. Okay, after this, we will get the current program break. This tells us where the heap currently ends. The last, or the last address of the dynamic memory, or the last address of the heap. So we will call sbrk with parameter 0 to get the current address of the end of the heap. And we'll store it in a variable called break. So this points to the end of the heap. Okay, we also have to add it in the header file, the function free. So function free void pointer. We changed the name from free to Sasta free because there's already a free function and it can lead to confusion. We also change it in the header file. Okay. And there's one more issue here. It doesn't know what the pthread mutex is. That is because we have not included the library. So include pthread.h. This is the library for using threads in C. This will work in Linux environment. Okay. Okay. So let's start writing the code for testing our functions, the sasta malloc and the sasta free functions. So I've made a small change here. I've put the header file and the .c file in the in a library folder, and I've changed the part accordingly. Okay, so let's first print out what we're trying to do. Okay, next we'll first sort out the first test. Here we allocate memory for integer variable, for single integer variable. So let's write the function first. The malloc function. Inside it will provide the size that we want to allocate. So it will be of integer size. We will store this inside a pointer variable or integer type, integer pointer. Call it pnum. We also need to typecast this. Okay, so then we've done this. Now let's put some print messages to see if it worked or not. If pnum if pnum has the value null, that means null value was put in pnum. That means memory was not allocated and memory allocation failed. So we'll print out the error message in this case. I will just write memory allocation failed. Otherwise, if pnum is not null, then we'll print out memory allocated integer variable pnum equals to. We're just doing this to show that it actually worked. This will have the value of the pnum. Okay, this worked. Next, we'll do the second test. Now we want to see if we can allocate memory for an array of integers. So in a similar way, we'll write the system malloc. Let's say array is of 5 elements, so we'll have 5 into size number of bytes in int, number of byte each integer variable uses. So this will allocate 5 into, let's say integer takes 2 bytes, so it will take 5 into 10 bytes of free memory, and we'll store it in an integer pointer. We'll store the initial address in a integer pointer called array, so that we can traverse it easily, and we'll typecast it in integer pointer. Okay, again we'll write some print messages to see if it worked or not. If array has null value, then it didn't work, and we'll write error memory allocation failed. Otherwise, uh, let's do something. Let's initialize the array. That way we can see if it actually worked or not. Okay, so the array. Okay, so in the array, let's say the value at the ith index is 10 times the index itself. So ARR3 is equals to 10 into 3, 30. After initializing, we'll put a print message. We'll say memory allocated ARR of, let's say, at the third value is, okay, it should work. Okay, now we do the final test 3. We will free the integer and the array memory. Okay, so let's write the function. First, okay. Here we will provide a pointer to the memory that we want to free. Okay, now let's print out a message here. Memory free. integer variable read. Similarly, we'll do it for the array also. Inside we'll put the array pointer and array memory read. Okay, so everything seems fine. Let's test it out. Sorry, there'll be a small change here. I forgot to assign a value here. So it's printing 0 because I haven't assigned a value. We're just doing this to check if memory has actually been allocated. So I'll give a value of, let's say, 12 here. That's all. Okay, so let's run the program and see if it's working or not. This is the website I told you about, CoCalc. It's basically providing a platform so that we can learn Linux terminal on here, and you can run programs in such a way that it's running on a Linux machine. Because I have Windows on my computer, and I didn't want to install Linux, so I can just use this to run programs as if it is running on a Linux machine. So I have uploaded my file here. The ones I programmed in VS Code, I have uploaded them here through this upload button. Okay, it's easy to do. You can do it here also, and you can open a terminal also. You can make terminal files. You can do lots of things here. Okay, so let's see. We are in the this folder only. Okay, so let's compile it first. We'll compile the main file and also the providing the path for the malloc.c file, and we'll store it in a program called we'll store it in an output file called my program. If we don't do this, it's by default the output file is saved as a.out by default, but we want to save it as my program. Okay, let's do it. No error. That means there's no current static errors in it. Now let's run it. My program. Okay, so memory has been allocated for the integer variable and it has been assigned the value 12 like I had given it. Memory has been allocated for the array and it has been initialized, and just as proof I've printed out the third index variable which is equal to 30. That's fine. And memory has been freed after that for the integer variable, and memory has been freed for the array memory.
Kmap